Hey folks, Eric Scheidel here again, the HVAC Service Mentor. Hey, welcome back to the channel and thanks for watching as always. By the way, are you a subscriber? If you're not, I think you should be. Go ahead and hit that subscribe button, hit the like button while you're at it, and don't forget to click the notification bell because we do HVAC videos like this on a very regular basis, and I'd hate for you to miss any. All right, so what are we talking about today? Today is going to be a bit more conceptual, and I feel that this is a very important concept for everybody who does service work and commissioning work and repair work on air conditioning systems. This is a very important concept to understand, and it is called the concept of sensible heat ratio, or SHR for short. Now, the better you can understand the concept of sensible heat ratio, the better you can understand the core of what makes air conditioning systems react and behave the way that they do. And that is going to do nothing but help improve your ability to service and troubleshoot them in the field. Now, what I'm going to do here is I'm going to start this off on a very, very basic level, and then I'm just going to get more and more advanced the longer I go. So if you've been doing this for a very brief portion of time, or you're not at all familiar with sensible heat ratio at all, you're going to really dig the first portion. And then at some point along the way, I might lose you, and that's okay. If you've been doing this for a very long time and you feel as though you have a pretty good understanding of sensible heat ratio, well, you're going to get more out of the ending part, and the beginning is going to be a little bit more basic to you. Regardless of where you're starting from, I do encourage you to watch this entire video. By the way, this isn't the kind of thing that you can just only half pay attention to. What I really encourage you to do is sit down and pay attention. And you may want to listen to this more than once over a period of time. I'll be perfectly honest with you. When I first started air conditioning, I had only the vaguest sense of sensible heat ratio. And as I have studied more and as I have learned more and grown more as an individual and as a technician, my understanding of sensible heat ratio and why it's so important to us as technicians has grown and evolved over time. And I expect the same to be true for all of you out there. So now that that's out of the way, let's lay down a couple of ground rules. What does this concept apply to? This is going to apply to conventional direct expansion vapor compression driven air conditioning systems. This means residential air conditioners and heat pumps of the standard split system design. This does not apply to ductless mini split systems. They do follow the rules of sensible heat ratio, but they're different, okay? Also, this applies to constant volume packaged rooftop units of any size as long as they are single zone constant volume systems. If you're working with a variable air volume system, things can change a little bit. There again, the basic concepts do apply, but they are just a little bit different. Now, because the conventional split system, direct expansion, vapor compression air conditioning system is still by far the most dominant and most common type of system that you are going to run into as a technician, I feel very comfortable using this platform to explain the concept of sensible heat ratio. So grab yourself a frosty beverage and a snack of your choice, dig in and settle in, and we will get right to it. In order to explain what sensible heat ratio is, I probably should cover some basic terms first of all, and a little bit of the basic ideas behind air conditioning. So first of all, sensible heat. What the heck does that mean? Sensible heat is heat energy that can be sensed by your skin, sensed and registered on a thermometer. And as we increase sensible heat or decrease sensible heat, we add it or we remove it, the temperature will go up or the temperature will go down. Measuring the temperature is how we notice or how we register or how we recognize a change in sensible heat. As our air conditioning system is operating and as it is producing the cooling effect, also known as the refrigeration effect, the temperature in the conditioned space will fall. We call this cooling, and that is a representation of sensible cooling or sensible heat removal. There's a second type of heat removal called latent heat or latent heat removal. Latent heat basically means that it can't be sensed or measured on a thermometer, and it does not make any difference in changing the temperature. For an air conditioning system, the latent heat that it is working on, the latent heat that it is absorbing, comes from water vapor that is absorbed into the air. Water vapor absorbed into the air manifests itself as relative humidity, also manifests itself as a measurement called wet bulb temperature. I'm not going to get deep into psychrometrics today. That's where wet bulb temperature comes from. That is going to be on a different video. So if you're wondering what the heck wet bulb temperature is, we will be referring to it somewhat, but we'll get much more deeper into that in a separate episode. So latent heat removal is represented by the energy that is trapped in water vapor, which is absorbed into the air. Everybody knows that as an air conditioner operates, it drops the temperature of the air. It also removes heat and drops the temperature of the conditioned space. Most people also recognize that air conditioners operate as a dehumidifier. Or at the very least, they know that there's a water drain that comes out of them and water is collected and it flows out of the drain. Well, the condensation and the accumulation and the draining out of this water is a function performed by latent heat removal. In order for water to transform from liquid form into vapor form, every pound of water has to absorb 970 BTU of heat energy. And that is what it causes it to transform from liquid water into water vapor. Water vapor is easily absorbed into air, and air is kind of like a sponge. So our air isn't just air, it's air plus water vapor mixed in. As our air conditioning system is operating, a certain portion of the cooling effect, or a certain amount of the BTUs that is absorbed by the air conditioning system, comes from the condensation of this water vapor. If it takes 970 BTUs to cause a pound of water to evaporate into vapor, the air conditioning system has to remove 970 BTU of heat energy from the water vapor in order to condense 1 pound of water and run it down the drain. So when we talk about the concept of sensible heat ratio, what we mean is, if I have, say, a 3-ton air conditioner, which is rated at 36,000 BTU per hour, and by the way, that is a nominal rating. Very rarely will it actually remove 36,000 BTU per hour. We'll look at that in just a second. But if I have a 36,000 BTU per hour air conditioner, a certain amount of those 36,000 BTU per hour is going to be dedicated toward dropping the temperature. That is the sensible heat portion. And another portion of those 36,000 BTU per hour is going to be dedicated to condensation or water vapor removal. That is latent heat absorption. So let's go ahead and take a look at some examples of how this works out. Because once you understand the basic concept that yes, that there are two different kinds of heat absorption happening. Yes, there is a division of labor between sensible heat and latent heat. There's a lot more to it than that. And there's a lot more to it really affects the way we analyze the performance of our air conditioning systems. So let's take a look. The first thing that I want to look at is a specifications sheet from a very common air conditioning system that is out there. This is for the Goodman GSX13 air conditioner. And for a large portion of the country, it is a very, very common unit to be found in residential and small light commercial applications. It is affordable, it's accessible, and they're literally just everywhere. One of the nice things about Goodman, from my perspective as a trainer, is that they give a lot of details about the performance of their units. And not everybody gives these details. Now, keep in mind that what we're going to talk about is Goodman's details, but all of the other major manufacturers, their details are very similar. They're just not published or presented in exactly the same way. We're going to look at what Goodman has to say about it, and keep in mind that every manufacturer does have published specifications like this. Some of them have more detail, some of them have less, and I like the way that Goodman presents it because it's relatively easy to understand compared to some of the other ones that you might run into out there. And it's also very easy to get. So this document is called the what do they call it? The spec sheet. This is the SSGSX13R43 spec sheet. It is, I think, 44 pages long. You're not going to find this in the installation and operations manual. You're going to have to go to the manufacturer's website and look for this specifically. Now, Goodman is very free with their information. Anybody can just go to their website, look at product specs, boom, there it is, and click the button and you have all of this information. Other manufacturers are a little more tight-lipped about it. You may have to be a dealer to be able to gain access to the special restricted site that has all these secrets posted on it. In which case you may need to either have a secret passcode or know a secret web address to get into. I'm going to jump forward to the product, to the expanded cooling data. That's what we want. So let's shrink this down a little bit and see what is it that we're looking at here. We'll move this out of the way. Over here on the right hand side, it gives us our expanded cooling data for the GSX13 and various sizes and various coil combinations. So the first page here details the GSX130181E combined with a evaporator coil of a CAPF1824B6DB. That is a mouthful. Let's go ahead and stick with our 3-ton idea, because a lot of folks are pretty familiar with 3-ton systems. And here we go. Now, you notice there are a bunch of different things. I'm not going to get all into these. What I really want to focus on is sensible heat ratio. And we're going to drill in here on this chart. If I can expand this a little bit. Over on the left-hand side, we see a column that says IDB. And there are various IDBs. There's 80, there's 85, and if we go further, there's 75, there is 70 above that. So it gives us an indoor dry bulb temperature range. This is a indoor dry bulb temperature of 80 degrees. This would be considered your return air temperature. We're given 3 different airflow selections. We have 1350 CFM, 1200 CFM, 1050 CFM. CFM stands for cubic feet of airflow per minute and has to do with specifically with how much air is going across. So we go across the top, shrink this up again. As we go across the top, we have outdoor ambient temperatures. And this is going to basically tell us the specific performances of this particular AC plus coil combination at a variety of indoor and outdoor temperature conditions. So going across the top here, we have 65 degree outdoor, 75, 85, 95, 105, and 115. You'll notice that there is a specific column or series of numbers that is kind of highlighted in green. These are the AHRI design conditions, also just simply known as design conditions. When the air conditioning system is rated, all air conditioners are rated under the same type of operating conditions. Why? Operating conditions can do and will affect air conditioner performance. It's very, very important that if you're going to analyze your air conditioning performance, you have to know the conditions under which it's performing. So we have to have that level of understanding. This chart will give us some idea of the different levels of performance we can expect from this unit when we have a variety of different operating conditions. Along this top here, ours is known as indoor entering wet bulb temperature. And you notice that we have 4 different selections for each outdoor temperature and indoor temperature combination. Essentially, wet bulb temperature is a representation of the heat energy contained in water vapor. And there's a real easy way to boil this down, pun intended. The higher the relative humidity, the higher the wet bulb will be for any given dry bulb temperature. If the outdoor temperature, or excuse me, if the dry bulb temperature was 80 degrees and the wet bulb temperature was 80 degrees, that would correspond to a relative humidity of 100%. As it stands here, we have an indoor temperature of 80 degrees and a variety of indoor wet bulbs at 59, 63, 67, and 71. This gives us a pretty good range of performances for this specific outdoor temp. Standard design conditions are 95 degree outdoor, 80 degree indoor, with a 67 degree wet bulb temperature. That is design condition, and that's why that is highlighted right here. So for every one of these categories, now we have a variety of specifications that are given, and here is what they are. The various performance specifications that are given are the number one, MBH. This stands for 1000 BTU per hour. This next column over says 33.1. That means 33,100 BTU per hour. This is also known as the total heat removal capacity of this AC under these conditions. S/T. This is the sensible heat ratio. What this means is a percentage or a ratio of the total. So this one is listed at 0.92. That means 92% of these 33,100 BTUs are going to be sensible heat absorption. Whatever is left over is latent heat absorption. And the sensible heat ratio will change depending on what the conditions are, and we'll look at that. The next column given is delta T. The triangle symbol means delta, which also means change in value of whatever comes next. Because the next symbol is a T, and T stands for temperature, this means change in value of temperature. This is also called your temperature difference, temperature drop, temperature split. All those mean the same thing. This means the difference between the return air entering the evaporator coil and the supply air leaving the evaporator coil. As we have said, there's going to be a temperature drop as the air flows across the evaporator coil, and that is called the delta T. So under these conditions, that delta T would be 23 degrees. Next one given is kW. This is an electrical symbol meaning kilowatts. How many watts of electricity are consumed by the condensing unit when it is operating under these conditions and producing this level of performance? The amount of electricity consumed by any air conditioner will change based on how many BTU it's removing and other factors that affect the performance, such as outdoor temperature, indoor temperature, and wet bulb temperature. This next one I get a chuckle out of because the more you look at specification sheets, the more you're going to find problems. And this one says /ANOS, which if it had an accent on it, it might be a Spanish word, but it is actually a typo. It's supposed to say amps. And this means how many amps will the condensing unit draw under these conditions. There again, that will change with the performance as it changes. High PR is high pressure, low PR is low pressure. So that's what we're going to be looking at. Now, let's go ahead and take a look at our design conditions values for those things and pay special attention to sensible heat ratio. I'll try to increase this for everyone in size, that is. There we go. Okay. So at design conditions for a nominal 3-ton AC, the total heat removal, as you can see, is 33,600 BTU per hour. Now you may notice that if this unit was specified as a 3-ton, 36,000 BTU per hour unit, 33.6 is something less than that. That is true. The way they rate these can vary from manufacturer to manufacturer. If you notice the next column up, when we get to a higher wet bulb value, we go from a 67 wet bulb up to, I believe that's a 71 up there. The total heat removed goes up to 35.9. It's about 36,000 BTU. So that's where that comes from. Our sensible heat ratio is 77% of those BTUs are going to be sensible BTU. The remaining 23% are going to be latent heat BTUs. The temperature drop will be 20 degrees. The kilowatts consumed are going to be 3.05 kW or 3,000 and 3,500 watts, 11.5 amps, 306 pound head pressure, 129 pound suction pressure. That is the introduction to sensible heat ratio. In our next video, we're going to take a closer look at examining sensible heat ratio and examining how differences in conditions and differences in airflow affect the sensible heat ratio. And more importantly, what does that mean to you as a technician who may be involved in repairing, adjusting, commissioning, setting up, or selecting new equipment for an installation project? So for now, this is Eric Scheidel, the HVAC Service Mentor. By the way, if you'd like to know more about this kind of advanced concept, check out my website at www.hvacservicementor.com. Take a look at the AC Masterclass. It's meant for technicians with 3 or more years of experience of dedicated troubleshooting and repair. So it is a little bit more advanced, but that is a great next step for you guys. All right, folks. Hey, don't forget to like and subscribe and hit the notification bell. This is Eric Scheidel, the HVAC Service Mentor, and I'll see you later. Thanks.